Large language models operate purely on mathematical probabilities, making their raw, unfiltered outputs inherently unpredictable when deployed in live production environments. When deployed without constraints, this unpredictability manifests as immediate system failures. A model might generate malformed JSON that crashes downstream APIs, or worse, hallucinate and leak sensitive personally identifiable information directly to an unauthorized user. There is a common assumption that sophisticated system prompts, or constitutional AI, will fix this. The belief is that if you simply instruct the model to behave safely, it will. But instructions are just more text. Against a targeted adversarial input, probabilistic instructions often fail. Relying exclusively on the model's internal reasoning for security is an architectural flaw. A standalone, naked model is not a complete software system. It is an operational liability. Production-grade safety requires isolating the model inside a multi-layered control plane. We build 4 boundaries around the LLM: input, retrieval, output, and action. Preventive controls stop unsafe requests. Detective controls identify policy violations. Corrective controls rewrite failing outputs. And operational controls log the pipeline. The objective is strict containment. We are taking a free-form, untrusted text generator and forcing it to operate as a highly controlled module within a larger, rigidly defined software ecosystem. This framework shifts the burden of safety away from the AI. By wrapping the LLM in external application logic, security enforcement becomes decoupled from the model's vulnerable, probabilistic reasoning. To see how this operates, we can track a user's request as it enters the system. Long before the prompt reaches the model, it hits the outermost boundary, the input safety layer. Classifiers scan the text for prompt injections, jailbreaks, and PII, shunting policy violations to an escalation queue. The surviving request enters the retrieval layer, pulling external documents to inform the model. These retrieved documents must be treated as untrusted external data. This retrieval layer has a dual mandate. First, it enforces access control at the database level, ensuring the system only retrieves documents the specific user is authorized to see. Second, it scans those retrieved chunks to sanitize any extraneous sensitive data before compilation. This strict sanitization ensures that a malicious command hidden inside a retrieved PDF cannot enter the context window and hijack the model's behavior. If you cannot mathematically verify the safety and authorization of the data entering the context window, you cannot secure the downstream model. Only after passing these preventative layers does the data reach the model itself. Here we apply internal safeguards using constitutional AI, guiding the model's generation using a set of explicit operational rules. These principles dictate how the model should format its reasoning. We can instruct the model to ask clarifying questions when user intent is ambiguous, or explicitly forbid it from fabricating citations when data is missing. The model enters a critique and revise loop. It drafts a response, evaluates it against a constitutional checklist, and cycles into a revision. But this layer has a structural limitation. Because it relies on probabilistic reasoning, an adversarial prompt can confuse the model and break the loop. Internal constitutional rules provide a necessary behavioral baseline, but because they can be manipulated, they are insufficient without external deterministic enforcement backing them up. This boundary is critical. The generated response leaves the probabilistic model and slams into the rigid, deterministic rules of the output validation layer. If the model hallucinates a text paragraph instead of an expected API format, schema validation enforces strict JSON contracts, blocking malformed structures. Next, grounding validation evaluates the response by comparing every generated claim against retrieved citations, ensuring no unsupported facts are introduced. Then, domain-specific logic is applied through business rule validation. This step ensures that a medical assistant always includes escalation language, or that a financial application never guarantees market returns. If the response fails any of these checks, the system triggers a corrective action. It catches the error internally, prompting a retry or an escalation. The user never sees the raw, unsafe output. This battery of output checks is the mechanism that formally converts a volatile large language model into a reliable, controlled software module. That level of control becomes mandatory when we move beyond passive chatbots. When an LLM is upgraded to an agent with access to live databases, web browsers, and external APIs, the risk profile expands exponentially. To manage this, agents require strict capability-based sandboxing. The model must operate under a policy of least privilege execution, given access only to the exact tools required for a specific task, and nothing more. The model never directly executes a tool. It proposes an action to the action layer, which validates parameters before execution. For high-risk operations, like deleting records, it enforces approval gates, halting execution and routing the action to a human for manual sign-off. In an agentic system, security decisions are entirely separated from the AI's internal logic. The model generates the intent, but the surrounding architecture holds the permissions. With these layers, we have isolated the AI inside a permissioned framework. Deploying this introduces a strict trade-off. As this graph shows, balancing helpfulness against restriction is difficult. If guardrails are too aggressive, the system suffers from over-refusal, blocking legitimate requests. A user asking for high-level cybersecurity education might trigger a threat classifier designed to stop hacking instructions. When the system repeatedly rejects safe queries, user trust deteriorates, destroying the viability of the product. To counter this, engineers implement safe completion. Instead of issuing a blunt refusal, the policy engine is designed to guide the model to provide safe, high-level information or redirect the user toward benign alternatives. A secure system that refuses to answer any question is useless. The engineering challenge is calibrating the pipeline to optimize for both rigorous boundary enforcement and high task completion rates. Even when properly calibrated, this multi-layered control plane is structurally static, while adversarial tactics and prompt injection patterns continuously evolve. This demands continuous red team testing. Engineers run automated jailbreak evaluation sets against the system daily, probing the boundaries to measure harmful compliance rates and identify new vulnerabilities. By capturing comprehensive audit logs at every layer, from the initial input to the final tool call, teams can monitor behavioral drift. Routing this telemetry back into the evaluation dashboard allows developers to adjust false positive moderation rates over time. Safety in production is never a single filter or a static list of blocked words. It is a living, multi-layered policy decision engine, enforcing the boundaries that allow artificial intelligence to operate reliably within a heavily engineered software ecosystem.